Hello again. Thanks for joining us. This is Space Nuts. My name is Andrew Dunkley. So good to have your company on this episode 318. Oh, my goodness. Today, we are going to be talking about a moon, not ours, not one of Mars's moons, not one of the better-known moons in our solar system. This is a moon that's been discovered, and they're sending out a probe to take a peek. Her name's Lucy. We're also going to look at the upside-down snow on Europa, which is weird science indeed. Plus, we've got a couple of audience questions, both focused on the James Webb Space Telescope. So we will tackle those stories and more today on this edition of the Space Nuts podcast.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me, as always, is his good self, Professor Fred Watson, astronomer at large. Hello, Fred.
Good day, Andrew. Nice to see your smiling face again.
Good to see you too. How have you been? What have you been up to?
It's been mostly fine. One or two glitches, but mostly fine. I wanted to tell you that our correspondent, it's probably the best name for her, in the United States, Heidi, who we mentioned last week, because she wants us to mention as often as we can the word lithopanspermia. So we did that, and I got a lovely text from her telling you and I that that we made her day, month, and year by mentioning our correspondence, which was lovely. So a good shout out to Heidi and her husband as well. And also I had the opportunity to chat on Monday night this week with our good friend David Astle.
Wonderful.
David Astle, the star of episode 301, who came to help us celebrate our 300th birthday, the ABC evenings presenter in Victoria, Radio Melbourne, ABC Radio Melbourne and Victoria. And I think David probably wins the prize for the ABC's most prolific promoter of the Space Nuts podcast. So he's a big fan, and it's always great to hear from him.
Oh, yeah, that's terrific. I'll pass on my regards, please.
Indeed, we will, yes.
I have a little bit of feedback too. I got a message on Instagram from Jet Swain saying, this is a big thank you to Andrew, who has kept my entertainment viewing going. When I thought I'd seen it all, Andrew put me on to For All Mankind, which I loved. That's a TV series about the moon. It's a sort of alternative history program. I really enjoy it, which she loved. And tonight I watched 13 Lives, which Andrew, like Andrew had me on the edge of my seat. You didn't say Colin Farrell and Joel Edgerton were starring. What a pleasure that was. Well, I didn't know who they were. I recognised faces, but I couldn't put names to it.
Oh, me neither.
Actually, when I was sitting there, I went, isn't that, what's his name? Judy said, Colin Farrell. I said, yes, thank you so much for your weekly inspiration. As a something-year-old corporate designer, I won't mention her age, I've become, during COVID, obsessed with the universe, Earth and beyond. I've binged all astronomy podcasts, and Space Nuts is by far my favourite, and not just because it's Australian. Thank you. Please keep the entertainment recommendations coming, Jet. That's lovely. Thank you so much, Jet. Lovely to hear from you. Now, Fred, let us get stuck into this week's episode proper. And Lucy is a good friend of mine, also a space probe, headed for an asteroid which has now been shown to have its own moon. Now, we've heard about this before, but what's significant about this particular situation?
That's right. We've talked about Lucy before. Launched last October, I think I'm remembering rightly, and it's heading out to passing through the asteroid belt between the orbits of Mars and Jupiter, and it will, in doing that, will actually fly by an asteroid, which will be its first visit. I can't remember which one it is. But then it is going to tour the Trojan asteroids of Jupiter. And remember, the Trojans are these two groups, actually, totaling about 9,000 asteroids, which share Jupiter's orbit, but they're clustered 60 degrees ahead of and 60 degrees behind Jupiter at the Lagrange points, the points where there is a gravitational well and things collect there. I think they're, if I remember rightly, it's L4 and L5. They're the two Lagrange points that share the same orbit as Jupiter. So this will be the first time that we've actually had the opportunity to explore the Trojan asteroids. Lucy will, I think, have a look at, I can't remember whether it's 6 or 7 of them, but it's a record number that it's going to fly by. It actually makes visits to both the leading Trojan asteroids, which, if I remember rightly, is called the Greek camp, and then there's the Trojan camp, which is the other one. I might have those the wrong way around, but it's going to visit both of those camps of Trojan objects. So a very exciting mission, which, as I said, we've mentioned before. But what's new and what's inspiring in its own way is that the Lucy team is continuing to make ground-based observations of these asteroids that it is aiming to target. And they're doing that by this technique called occultations, where what you look for is the shadow of the asteroid cast not by the sun, but by a star passing across the Earth's surface. So as the asteroid passes in front of a star, the star's light is blocked out by the bulk of the asteroid. And this is called an occultation, from the word occult, which means to hide. So the asteroid hides the star. If you think about the way this works, there's the asteroid's passing in front of the star, so its shadow is moving along the Earth's surface. And if you line up a whole lot of observers basically on a line that is at right angles to the path of the asteroid, then what you're going to get is different samples of the shadow passing over the Earth. And it's actually a great way of mapping asteroids, because you can, by timing it very accurately, you know how fast the asteroid's traveling. By timing its disappearance and reappearance in all these different shapes, you can get a really good idea of the dimensions and actually the shape of the asteroid. And so that was happening. They did that, the Lucy team, some months ago. I can't remember. Beg your pardon. No, it was back in. Yes, it was. It was in March this year. And it's one of the target asteroids for the Lucy mission. It's the smallest of them, actually. It's about 26 kilometers wide, a tiny object, considering how far away it is. And it's called Polymele, Polyemele, and that's an ancient Greek name. And so I looked it up to discover what it means. It means many sheep. Yep, many sheep, Polymele. Okay. So in ancient Greek, so we've got the asteroid Many Sheep being visited by Lucy, but the surprise in their observations of Polymele in March was that there was a second dip in the light of the star, or fall in the light of the star, shortly after the main dip by the Polymele asteroid itself. And that is being interpreted, I'm sure correctly, as a moon of this object, which is about 5 kilometers in diameter. That gives you an idea of how sensitive this technique is, the occultation technique, because something 5 kilometers in diameter at a distance, it's going to be roughly in the region of 800 million kilometers, because that's the sort of average distance that Jupiter is from the sun. Then what they are likely to do following up on that is to use the Hubble telescope. I don't think that's yet happened, to essentially confirm the the existence. I mean, I don't think there's any doubt about the existence of this little moon, but to confirm its orbit, to look at how it changes, how its position changes over time, because it will orbit its parent object, Polymele, and I think that, that's such a great testimony to the power of the occultation technique and what you can do from Earth with these objects, which are minuscule. The Science SciTech Daily website, which reported this, has a very nice comparison that what you're looking at when you think about this tiny object at that distance, it's the equivalent to finding a quarter, American coin, on a sidewalk in Los Angeles while you're on a skyscraper in Manhattan.
Wow.
The other side of the country. So it's fantastic resolution. And as I said, it's what you get when you do occultations.
So if these two things, you ready for this dad joke?
Oh, here we go.
If these two things hit each other,
yes,
the asteroid and its moon, would that be a polymele?
Oh, I like it. It would certainly be a very woolly occasion.
Dear, oh dear. I feel very sheepish now. Is it more likely, though, that polymele or polymele or whatever we want to call it and the other object are tidally locked?
Very likely. Very likely. That would be pretty hard to confirm, but that's nearly always the case with these asteroids and their moons, which are actually quite common, Andrew. It's not it's not a rarity. Even though I didn't mention this figure, the little moon, whatever it's called, it hasn't got a name yet. Even though it's about 200 kilometers actually from Polymele, I think it's likely that they will be that at least the moon will be tidally locked, so it always faces the same side to Polymele. Whether Polymele itself is tidally locked is a different question, because a 5 kilometer moon is pretty small compared with an object that's 27 kilometers wide. So,
Do we know what Lucy stands for?
No, it's not an acronym.
It's not.
It's named after Lucy, the hominin that was discovered in Africa.
Right. The parent of humanity.
That's right. Yes. And it's partly because it's an origin story. The asteroids are all about the origins. These Trojan asteroids, we hope, will tell us about the origins of the solar system, actually, because they're very ancient objects, as was Lucy. And of course, Lucy got its name because when the discovery was made, the team, the archaeological team, spent the whole night celebrating with the Beatles song, Lucy in the Sky with Diamonds. Yeah. That's where it came from. So, and if I remember rightly, I'm remembering now from when we talked about this last year, Lucy itself, the spacecraft, carries a plaque which has various bits of poetry on it, including from the Beatles. So it's a really nice, very, very nice little tie-up of what it's all about. And I'm sure we'll hear more of that kind of thing when the spacecraft gets out to the asteroid belt.
Elton John does a fantastic cover version of Lucy in the Sky with Diamonds. It's a big hit for him too. I'm going to refer back to Jet, who I mentioned at the beginning of the show, who enjoyed my my movie and TV show recommendations, and that has dovetailed perfectly here because the movie Lucy is well worth watching. It's got nothing to do with space or astronomy, but it's a science fiction movie about a drug that can enhance your thinking, and Scarlett Johansson stars in this particular film with Morgan Freeman. It is fantastic.
Okay.
I've watched it probably 3 times now. I really love that film. So give that one a try. It's called Lucy, and it is based on the premise of the origin of humanity, and Morgan Freeman plays a professor who's looking into the workings of the human brain and what it would be like for people to increase the amount of brain power they use. Humans only use 10%, and well, without giving too much away, Scarlett Johansson's character Lucy gets to 100%. and you can imagine what happens from there. But
That sounds
really
intriguing.
great film, Jet.
Yeah,
So
sounds
check it out.
intriguing.
It's I'm sure you'll enjoy it. Let me know what you think. And the only downside with this Lucy mission is how long we've got to wait, because it's not going to get there for a little while yet.
No, it's towards the end of the decade, I think. But
it is.
There will be stuff comes back as it passes the its target asteroid in the main asteroid belt, which, if I remember rightly, also has a moon.
Okay.
I can't remember which one that is, but actually, no, I might be wrong there. I think it doesn't have a moon, but certainly at least one of the other Trojan asteroids has a moon that's been looked at. So
right.
it's going to be a really interesting mission.
Yeah, and I'm also staggered by the number of asteroids that are out in that vicinity. That's a big cluster of crashing into object things.
Yes, that's right. Exactly, that's right. So they've got to find their way through all that. Absolutely.
All right. There'll be obviously more news on the Lucy mission in years to come, and maybe sooner than that. We'll certainly keep an eye on it. This is Space Nuts. You're with Andrew Dunkley and Professor Fred Watson.
Space Nuts.
From one moon to another, Fred, as we head to Jupiter's ice moon Europa. This is one of my favourite places in the solar system because of all that it promises in terms of discovery. And one such discovery has been made, and this one's just weird science. This is all upside down. Left becomes right. Dogs and cats are living together. It's just out there. This one.
You're hitting holes in one. Yeah, it's an extraordinary world. Yeah.
Not recently, but I have three. See, look, 1, 2, 3.
Oh yeah, I see them. Yeah, good. They look like moons of Jupiter, actually, the way they're lined up there.
Those ones have collided with a lot of things, though.
Yeah. So Europa, one of the 4 Galilean moons, the moons discovered by Galileo back in 1610, and like many of the moons of the giant planets, or like several of them, perhaps many is the wrong word, Europa has this structure of a rocky object overlain with a global liquid water ocean with a thick layer of ice on top of that. And what has prompted this study is the fact that NASA will be launching a spacecraft in 2 years' time to explore Europa, not to land on it. It's actually an orbiter. It's called Europa Clipper, and it will have lots and lots of scientific instruments on board to probe the details of Europa from above. Which is the safest way to do it, and will probably give us some really good insights. Now, part of this sort of entourage of equipment that the spacecraft will carry is an ice-penetrating radar. So that's going to be one of the important aspects of this, because we want to know what's in the ocean, basically, and what it's like. And so
I'm betting on krill.
Yeah, it could be krill. Yeah. Could be, well, I don't know whether the ice-penetrating radar will detect that, but you never know. Large bodies of krill might produce a radio reflection that would move around under the ocean. Who knows? However, the design of the ice-penetrating radar has to know kind of what sort of ice you're dealing with.
Of course, because there's all sorts of different kinds.
There are, that's right. And so the ice crust is thought to be 15 to 25 kilometres thick. It's not a thin layer of ice by any means. The ocean's thought to be much deeper, actually, that maybe 60 to 150 kilometres. This comes from, observations made of the properties of Europa, in particular things like the magnetic properties, because that's one of the things that tells you about the presence of water. So the team, as I said, working on the radar, wants to know about what the ice that they're going to find there. And that's because, as you said, ice comes in many different forms. But with ice sheets, there are two definitely distinct forms of ice formation. And one of them's got a really nice name. It's called frazzle ice.
It's called what?
Frazzle ice. F-R-A-Z or Z-I-L. Frazzle. Not frazzle as in I'm feeling frazzled, which is a different spelling, but it's called frazzle ice. And frazzle ice is basically ice that forms by this process that I think you alluded to a minute ago, upside down snowfall. So it's ice crystals in the water, which are basically rising upwards and sticking in a sort of frothy manner to the underneath of the ice sheet. That's how the ice sheet's growing, by this frazzle ice. It's an accumulation of ice crystals that sort of builds up underneath these sheets, and it's quite fluffy. It's not solid ice. I'm sure it compresses to become solid ice over time, but that's the way it's formed. The other way, it's a different sort of ice, which has a different name. It's called conglomeration ice. Congregation ice, not conglomeration, congregation. And that's ice that it basically builds up downwards from the underneath of the ice sheet. The congregation ice is building up downwards. The frazzle ice is building up upwards, if I can put it that way. And the reason why it's important, and this is stuff we know from ice sheets here on Earth, from Antarctica and places like that. The reason why it's important is the salt content of these two different sorts of ice is very different. Congregation ice contains 10% of the salt in the seawater from which it's made, whereas frazzle ice contains only 0.1%, 0.1% of the salt. So one's nearly pure water and the other's quite salty. And so that means that they will have different reflective properties when you're designing the radar. And so that's why this study is being carried out. And I think the current thinking seems to be that at least in part, the frazzle ice is actually the mechanism by which these icy crusts are built up on these little worlds deep in the solar system. So the suggestion behind that then is that the ice sheets that have been built up from that are less salty than was believed before, and that has implications for the radar. So I think what they're going to have to do with this radar is design it for all contingencies, that it will show up reflections no matter what the salt level of the ice is underneath it.
Has this upside down ice been confirmed, and if so, how do they know if it's happening under the water and under the ice, or is this just a theory?
It's confirmed on Earth, but not on Europa. So that's you're right. It's a theory. What they're doing is looking at the conditions that might exist on Europa and looking at the physics of that and trying to decide how that relates to these different ice formation mechanisms on Earth. So it is a suggestion rather than solid knowledge, and that's why I think that the mission scientists are going to be looking to make the radar equipment as broadly receptive as possible to different levels of salt in the ice.
It prompts another thought. If this ice is forming in whatever way on Europa and in Europa, does that mean that the ice is getting thicker, or is there some sort of water cycle where it melts and refeeds the oceans?
That's a really good question. I assume.
I thought so.
That is. It's a great question.
I should be a journalist.
You should be a physicist, Andrew.
I don't think so.
There's, you would imagine that there is some sort of cycle, and I guess what we're talking about is, I don't know, the formation of the ice on Europa. It's been there a long time. It may even be truly ancient ice that dates from the earliest history of the solar system, a bit like the ice that we find in comets. I'm struggling to answer this, because I think Europa as do some of the other moons certainly those Galilean moons, particularly Io, of course. They have their own internal heat mechanism. With Io, a lot of it's due to tidal friction. It's being squashed and stretched by Jupiter's gravity. So, but the bottom line is that the interior of Europa, where the rocky core is probably warm, and that probably does cycle the ice, because there's clearly heat loss taking place from the surface, because that's facing outer space, and anything that's got temperature, and the ice certainly does have temperature, even though it's very cold, it radiates into space. So I don't know the answer, though, to whether the ice sheet is getting thicker constantly. Maybe if you think about it intuitively, as Europa cools, and maybe it is cooling over time, I mean, talking about geological time here now, as Europa cools, then you're going to get more of that water freezing, and so yes, the ice sheet might be building up to be thicker. There you are.
One more.
We got there in the end.
Yeah. One more question though. We know how the planets form, with all the dust compacting in on itself and etc. What about an ice moon? How would an ice moon form?
So it's obviously a stepwise process. You form the rocky core first, and that's quite hot to start with.
Yeah.
But then the solar system is so beyond the orbit of Mars. That's outside the habitable zone. It's outside the zone where liquid water can exist on a surface.
Yeah.
And you're within the zone where any water vapor would freeze to become ice. So probably even when the nebula itself, when the sun was just a baby star, there was probably condensation of that ice onto these surfaces. But my guess is that a lot of that ice has come from the outer solar system, from the Oort cloud, which is really the residual sort of freezing of that water vapor that's formed these lumps of ice, which we call comets. Those have been flying into the inner solar system for the last 4.6 billion years, bashing into things like the Earth, and maybe that's where our oceans came from, at least in part, and possibly it's where the oceans of Jupiter's moons and Saturn's moons came from too. And in fact, one of Neptune's moons has the same structure.
Okay, yeah. It just seems strange to me that with all the ways planets form, that you could have a couple of moons in our solar system that were just, they're more or less just water in one form or another. And
they've still got a rocky core. Most of their mass is in the core.
Yeah.
But you're right. There's twice as much liquid water on Europa as there is in all the oceans of the Earth. It's a staggering statistic. Yeah.
It's amazing.
Yeah.
Hopefully we'll learn more. I'm still looking forward to them giving the go-ahead to the submarine mission.
Yeah, that's right. Got to get into the water.
I hope that happens one day.
It's the drilling through the 25 kilometres of ice that's the tricky bit.
Yeah, they could just use heaters and just let it sink.
Well, that's one of the ideas. A bucket.
Yeah, there you are. So I should be a physicist.
A bucket of plutonium dropped on the surface that it only take about.
But that sort of brings into the ethical.
Yes,
the ethical question.
Exactly.
Polluting other worlds.
You're going to fry anything you've
our nasty stuff to them.
Yeah,
we've got enough nasty stuff.
Yeah, I agree with
that.
All
right, we will watch with interest when they discover new things about Europa and beyond. This is the Space Nuts podcast. Well, it's a podcast if you're listening on a podcast. Otherwise, it's a radio show. But thank you for joining us. This is Andrew Dunkley. That's me, and Fred Watson, who is an astronomer at large. He knows all the stuff we need to know.
Space Nuts.
Now, Fred, my favourite part of the show, where we turn it over to the audience and they ask us all sorts of amazing questions, and we refer to other people and get back to them in a couple of years, or we answer them instantaneously. You're going to love this. I love people who just show enthusiasm for a topic and do it in a very demonstrable way, and that's certainly the case with Billy in New Jersey.
Professor Watson, Andrew, Billy Gerard in great New Jersey in the U.S. of A. Hey, quick question. I recently saw the James Webb, the brand new space telescope, has seen a galaxy far, far away. One they're saying may be older than the 13 blah, blah, blah billion years we think the universe is. Does this mean our estimate for how old the universe is may be wrong? And a follow-up to that, if that is the case, do you think, Professor Watson, the square kilometer array may see something even older still? Billy Gerard over here in New Jersey, the great USA. By the way, love the program. As we used to say around here, dittos. Thanks, appreciate the show. Keep up the good work. Over and out.
Thank you, Billy. What's the game show that you host? I want to watch. So I love your enthusiasm. It's fantastic.
Absolutely. It's great stuff.
And I hope all is well in the greater state of New Jersey. Now, the James Webb Space Telescope throwing up all sorts of images and, as a consequence, all sorts of questions. So the image of a galaxy that may be not only far, far away, but older than perhaps even the universe. And does that suggest we've got the age of the universe model wrong?
Yes.
I guess that's what James Webb was sent up there to find out.
That's right. So I haven't seen that report, actually. Everything I've seen is pretty self-consistent. So what gives us the age of the universe is, first of all, the expansion of the universe. We can look at the expansion today and investigate how fast the universe was expanding in the past, and then extrapolate back, and we get 13.8 billion years. But we can also look at the flash of the Big Bang, the cosmic microwave background radiation, this radio signal that's pretty uniform all over the entire sky, which we interpret as having such a great look back time. In other words, we're looking back so far in time that we're seeing when the universe was still glowing brightly. So this is a sort of wall of radiation that corresponds actually to the time when the universe became transparent, which we think was about 380,000 years after the Big Bang. So that cosmic microwave background is, I sometimes call it the cosmic wallpaper, because it's a background against which everything that we see in the universe is projected. And it corresponds to seeing back to the time of the Big Bang. So anything in front of that must be more recent than the Big Bang. That's the logic. And, galaxies, their ages are determined principally by what we call the redshift, which is the time, the amount by which their radiation has been stretched, because we know what frequencies hydrogen emits light on when it's excited. We know that, in fact, the wavelength of the light is the same thing, just putting it upside down. The wavelength of the light when it was emitted, and we know the wavelength of the light when we receive it. And by comparing those two, we can work out how much the universe has expanded in the meantime. I'm trying to get my head around, though, the idea of a galaxy that might have pre-existed before the universe. So this flies completely in the face of all that we know about the way the universe behaves. But whether you could have something that was there before the Big Bang, and my guess is it doesn't work. The logic simply doesn't let you do that. And so if you've got a galaxy whose age, the age is always going to be, the look back time to the galaxy is always going to be less than the age of the universe. And so if there are figures that are incompatible, then we've got something wrong. Now, that's not new, Andrew, because when people started looking at the age of the universe at first in the 60s and 70s, there was a time when it looked as though the universe was relatively young, maybe 10 billion years old. But that was totally counterintuitive, because we know that some stars are much older than that. We know, by the way atomic processes work, the decay times of nuclides when they decay. We know it's like the carbon-14 dating that we use for vegetable material here on Earth. You can get an age from it, and so we could get ages for these stars which turned out to be more than what we thought the age of the universe might be. And that clearly doesn't work. And yes, it turned out that we got the age of the universe wrong, because the universe is not slowing down in its expansion. It is actually increasing. So a really great question there from Billy. And I will try and find any reports that suggest that we're seeing galaxies that are older than the universe, because I'd like to know how those are reconciled.
But analysis of the cosmic background radiation, mathematically, they've got it really fine-tuned as to when the Big Bang happened, and that's right. The dawn of the universe, isn't it?
It ties. That's right. That you can tie down that flash of the Big Bang, the cosmic microwave background radiation, very well with what we learned from the expansion of the universe. The two things are quite compatible. So my guess is we haven't got things badly wrong, but there might be tweaking needed for the numbers themselves.
Yeah, and I suppose it brings, because of the substantial amount of time we are discussing, how much time is a workable error that takes you into a new realm. I have found a story in newscientist.com that suggests James Webb has found a galaxy that predates the earliest known galaxy. Yes. So now they're saying the first galaxy, or this galaxy that's been discovered, formed 300 million years after the Big Bang, and that there was, the previous oldest galaxy was 400 million years after the Big Bang. So the timing still correlates in terms of the Big Bang happened and then the galaxies formed. Yeah,
that might be it, actually. And you're quite right. I did see that report that suggests that, and it's still a problem for the theoretical physicists who try and work out what the conditions were after the Big Bang, and then how long it would take stars to form given those conditions and galaxies to form. And so that just means that you've got to rethink the length of time. It's the period, by the way, between the Big Bang and the first stars is what we call the Dark Ages. And indeed, as Billy mentioned, the Dark Ages are very much the province of the square kilometre array when it comes online towards the end of the decade. That's one of the reasons why it was built, to look at the way cold hydrogen was distributed in space in a time before the first stars and galaxies formed, because radio signals were emitted by cold hydrogen, whereas light wasn't emitted because there wasn't anything shining. So it is interesting. What it means is the Dark Ages period is, as we push back the age of the time when the first galaxies were formed after the Big Bang, then you're shortening the era of the Dark Ages. And of course, that means you're seeing, the signals are going to be fainter and fainter. So it's a challenge for astronomers to discover these things so far back in time.
So another bad dad joke coming up. So during the Dark Ages, there were no stars. Therefore, there was no light. Therefore, there were only nights.
Oh. It's a good one, though. It's a good one. I like it.
Oh, dear.
I like it. But because there was no light, they weren't in shining armour, though.
No, they wouldn't have been, would they? Oh, dear. Okay, Billy, thanks for the question. The answer is no, apparently, at this stage. But watch this space. All right, let's move on to our final question. Not sure who this is, but it's another James Webb Space Telescope question, but we're talking more physics and telemetry this time.
Hey guys, I love your podcast. I've been listening to you for about a year now. I've learned so much since. So what I want to ask about is the JWST orbit and field of view. So the JWST creates a circle around this L2 point, which I would like to call the JWST ecliptic for point of argument. So how far out of this field of view, out of the ecliptic, can it see? And I want to know when this ecliptic will reach the point where JWST can see the center of the galaxy. That's something I'm really interested in. I hope I made sense, kind of making up my own terms. Thank you, guys.
Okay. Thank you very much. That's a good question. I think we've talked about how the James Webb Space Telescope moves in the Lagrange point, but there's a lot more in that question than we've probably looked into before. So I saw you nodding. So obviously you were enjoying unraveling.
Yeah, no,
this
it's a great question, and most of which I do know the answer to.
Oh, good, because I haven't got a clue.
So our anonymous listener is absolutely right. The telescope is in orbit around the L2 point, 1.5 million kilometers on the side of the Earth away from the sun. So it orbits that point. But the issue here is, Andrew, that it's always got to keep its sunshade, and that's the tennis court-sized array of 7 or 8 different layers of shading material, shade cloth, if you like. That's always got to be pointing back to the sun, so that the telescope itself is never lit up by the sun. And so now, if you think of that sunshade, and you probably imagine, most of us have seen pictures of what the telescope looks like. It's got this giant 6.5 meter mirror, which is facing sort of parallel to the sunshade. That's the structure of the telescope. And it's fixed, is that. The telescope doesn't move with respect to the sunshade. But to point the telescope, you tilt the whole thing. And so what you've got to think of, I'm trying to avoid using my hands to describe this, Andrew, because not everybody can see my hands, but I'm going to do it anyway. Here's the sunshade. The telescope's pointing this way. The sun's in that direction, beaming its light onto the sunshade. So you can actually tilt the telescope and within a certain amount, and I can tell you what that amount is, it's 39 degrees, so that you've got a coverage of 39 degrees in any one direction. But then you can also rotate it. This is so you're always keeping the sunshade pointing to the sun. So what you've got is this sort of donut-shaped region of the sky, which is, you could call it, as our listener calls it, the JWST ecliptic, because the ecliptic is the path of the Earth around the sun. That's the ecliptic plane. So you've got this donut, which the James Webb Telescope can see at any time just by tilting itself slightly backwards and forwards in the direction towards the sun, or being rotated around an axis that connects the telescope with the direction to the sun. So you've got this area of coverage. I don't know how many square degrees it is, but it's 39 degrees multiplied by 180, because you can go all the way around. So as I said, it's a donut shape. But then, as the telescope, as the Earth plus the L2 point orbit around the sun, the angle that donut makes with the sky changes. And so over a year, the telescope has access to the whole of the sky. And what that means is that at some time within the first year of observing, and it started pretty well once they'd got things set up in March or thereabouts. So within that year, it will reach the galactic center. It will have access to the galactic center. And I'm not sure when that will be, because I haven't looked at the details, but it is coming up. It may even have already happened. We might have already got observations by the JWST of the galactic center, which is still being processed. But it will happen, and it'll happen within a year. So it's a very, very clever arrangement, to keep this telescope cold, protect it from the radiation from the sun, but still have access to the whole sky. And whilst you don't have that instantaneously, you do have it over the process of a year.
The galactic center is, invisible to us because of the dust. Traditional observation methods have given us nothing, basically. Although we recently created an image of Sagittarius A star, but will James Webb get through that dust? Will we be able to actually see galactic centre?
Yes. So that's how we know that there's a black hole there to start with, because infrared telescopes, excuse me, on the ground, principally the Keck telescopes in Hawaii and the Very Large Telescope, individual unit telescopes down there in Chile, the European Southern Observatories facility, they've both got infrared capability, not as good as the James Webb because there's still atmospheric absorption, but it's using that has allowed astronomers, two groups of astronomers, both of whom have now won Nobel Prizes, to watch stars orbiting around the black hole in the galactic center. And that was all done with infrared radiation. And so the James Webb will see those stars. It will actually resolve the stars near the galactic center. That's why our listeners are so keen to hear about it, I'm sure. But of course, the movement of those stars has now been observed for more than 20 years, which is how we know they're orbiting around this invisible point, the black hole. The Webb won't see that, at least not in its first pass. Maybe, I think the Webb is probably going to have about 20 years of life. I would guess that every time the galactic center comes into its field of view or its availability of view, we will get another snapshot of these stars in the galactic center and might get some marvelous detail about the way they behave and give us a better estimate of the mass of the black hole, currently estimated about 4.6, I think, million times the mass. Sorry, no, it's a bit less than that, roughly 4 million times the mass of the sun. 4.1, I think it is. Sorry, I can't remember the number, but it's a big supermassive black hole, and we're learning far more about it. And of course, as you said, the Event Horizon Telescope gave us the first image of the material around it. So a great question, and
fabulous
with a good
question.
answer too, because it's going to happen.
Yeah, can't wait. That'll be really exciting news. All right. Thanks for the questions. Thanks for listening. We're going to wrap it up for another week. Thank you so much, Fred. Oh, by the way, if you do have questions for us, we do have a little bit of a shortage at the moment. So if you do have a question for us, jump on our website, spacenutspodcast.com or spacenuts.io. They both go to the same place. Click on the AMA tab where you can send us audio or text questions, or click on the Send Us Your Voice Message tab on the right. And if you've got a device with a microphone, it's as simple as pushing the button saying, "Hi, I'm Joe Bloggs. I'm from Upper Combukta West, and here's my question," or whatever you like. But we do love to know who you are. Also, while you're on our website, there's Astronomy Daily, which is constantly updated with astronomy news. Don't forget to visit the Space Nuts shop. There's plenty of goodies in there. And plenty more to do on our website. And of course, if you're into social media, there's the Space Nuts Facebook group, there's the Space Nuts Instagram page, and the user-created Space Nuts podcast group on Facebook, which was created by listeners. Hi, Carrie. And it's just a place for listeners to get together and chat and ask each other questions. So jump on there as well. But we're going to wrap it up. Thank you again, Fred. Great to catch up.
Always a pleasure, Andrew. See you soon.
See you next week. Fred Watson, astronomer at large, part of the team here at Space Nuts. And thanks to Hugh in the studio, who forgot we were on today. Cue the crickets. From me, Andrew Dunkley, thanks for your company. Look forward to catching up with you on the very next episode of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.